In our most recent videos, we've introduced the notion of parametric equations and looked at a number of examples of curves that can be described parametrically. Today, I'd like to begin talking about how we can play calculus in the setting of parametric equations. Let's go to the whiteboard. To begin, I'd like to, just remind ourselves what a derivative is, right? By definition, a derivative is the limit of this quotient, right? This idea of a couple of y values changing as corresponding x values change. We usually use a picture that looks something like this to do the job. So we have a function that I'm calling f, and focusing in on a point x here, and then we perturb x a little bit, right? We move it just a little bit, some little delta x distance to get to another point, and we look at the tangent line between the point at x f of x and the point at x plus delta x and its functional value. And so its functional value, of course, is f of x plus delta x. The functional value is f of x. So this is the difference in y value, so a delta y, and we're dividing it by this change in x. So this gives us the slope of this secant line, and the derivative is defined by letting delta x get tiny, right? Bring our x plus delta x toward x, and look at what the slope of the resulting secant lines are getting closer and closer to in the limit. Right? This is often abbreviated, right? We often use dy dx, but sometimes this is abbreviated by writing the limit as delta x goes to 0 of, and instead of writing all of this, right? It is just a change in y values. We just go ahead and write change in y, where it's understood that delta y means that that difference in the y values that are indicated on the diagram. Okay, so with that in mind, we want to go to the parametric setting. So we're letting x and y be defined like this. You may recognize that this is our definition of the cycloid. These are the parametric equations that gave us the cycloid that we talked about a couple of videos back. And so my question is, first of all, does it even make sense to talk about the derivative of y with respect to x? Does it make sense to talk about dy dx whenever we've got x and y both defined in terms of different functions? Well, yes, actually, it makes perfect sense to talk about it, because after all, we're looking at this picture of y against x. And so it certainly makes sense to ask, what is the slope, right? That's what dy dx means, right? What is the slope at a particular point, right? So, what's the slope of this curve at this point? Here it looks like the slope of the curve is 0 here at pi r. Keep in mind that the length of one period is going to be the circumference of the circle that generates the cycloid. Remember how we had generated this? We started with a point on a circle, and then we rolled the circle along this line until the point that was right here at the origin comes back to the x-axis again over here. And so this distance right here is going to be the circumference of my generating circle, which is going to be 2 times pi times the radius of that generating circle. So here at pi radians, or at the x value of pi times the radius, it looks like the slope of the tangent line is going to be 0. I'm not sure what it looks like the slope is going to be here at 0 and at 2 pi r. We'll we'll investigate that a little bit later. But I think we can agree that it at least makes sense to ask, what is the slope of the tangent line at various points? What is dy dx? So yeah, the question makes sense. It's just a matter of how are we going to compute it, right? How can we calculate dy dx when x and y are expressed in terms of this third variable, in terms of this parameter, theta? Well, here's a very non-rigorous explanation as to how we're going to make sense of dy dx in the parametric setting. So we've already talked about dy dx being equal to the limit of the change in y's over the change in x's as delta x becomes small. And so what that means is, whenever delta x is really, really tiny, the derivative is going to be very, very close to the slope of this secant line, right? So again, dy dx is actually the full derivative, the limit, as delta x goes to 0, right? So if delta x is tiny, the quotient of these two numbers is going to be very close to the derivative. Well, I've got a fraction here. I can certainly divide top and bottom of my fraction by some number. So I'm thinking of delta theta, right? I'm looking at a little change in the parameter. I can certainly imagine a very, very tiny number, delta theta, and I'll just divide numerator denominator by it. That's equivalent to having multiplied delta y over delta x by 1, right? And so if delta theta is tiny, well, then this numerator ought to be very, very close to the derivative of y with respect to theta. And that certainly makes sense to take, right? The derivative of y with respect to theta, I can certainly find. And the denominator here is going to be very, very close to the derivative of x with respect to theta, right? And so, and again, that makes sense to evaluate as well, because x is defined in terms of theta. And so what we have is that a reasonable definition for the derivative of y with respect to x in the parametric setting is to look at the derivative of y with respect to theta and divide it by the derivative of x with respect to theta. And that's exactly what works. I'm not going to go into a rigorous proof of this. What I've just outlined is the general idea for why this definition is appropriate. Okay, so let's look at an example. Let's go back to the cycloid. And let's just go ahead and evaluate the derivative of y with respect to x. So by the definition that we gave just a moment ago, the explanation that told us how it makes sense to evaluate dy dx, let's go ahead and take the derivative of y with respect to theta and the derivative of x with respect to theta and divide. Well, let's see. Here's y. And so the derivative of y with respect to theta is going to be r times, remember r is just a constant, that's the radius of our generating circle, r times the derivative of 1 minus cosine theta. Well, derivative of 1 minus cosine theta is 0 minus a negative sine theta. And so that's, in total, numerator is going to be r sine theta, right? dy d theta is r sine theta. dx d theta is going to be r times the derivative of theta minus sine theta. So r times 1 minus cosine theta. And r over r is just 1, so I'll factor out a 1. And I'm just left with sine theta divided by 1 minus cosine theta. So I'd kind of like to make sure that what we got here actually agrees with our intuition, agrees with what we would expect to happen with the cycloid at various points. So let's just notice that here at pi times r, actually knowing what the x value isn't going to be the most convenient thing for us, right? Because dy dx is actually entirely in terms of theta. But let's see, pi times this x value happens whenever we are halfway through our rotation of the circle. So circle has 2 pi radians in it, so halfway through we're going to be at pi radians. And it looks like we should have a slope of 0 at that point. And let's just see what that gives us. So whenever theta is pi, well, whenever theta is pi, the numerator here is sine of pi. The denominator is 1 minus cosine of pi, right? Well, let's see. So sine of pi is 0, and cosine of pi is -1. So my denominator is 1 plus 1. Well, so whenever I evaluate the derivative at theta equals pi, I get 0 over 2, which is 0. It's exactly what I expected. Slope of 0 sitting there. What about it at 0? We wondered about this point a moment ago. Well, let's just look at it. So sine of 0, well, that's 0. 1 minus cosine of 0. Cosine of 0 is 1. Oh, so I'm gonna have to do a little more work. It says that the derivative of y with respect to x is 0 over 0. Well, that's undefined, but it doesn't mean I can't evaluate the slope, right? I have a form that I could apply Bernoulli's rule to, what most people call L'Hopital's rule, but Bernoulli invented it. Let's call it Bernoulli's rule. And so let's look at what happens as theta approaches 0. Instead of just trying to evaluate it and getting an undefined form, let's see what happens as theta approaches 0. And we're going to do it from the right-hand side because I'm imagining working in this period of the cycloid right now. So I'm imagining coming at it from this direction. So theta approaches 0 from the right. Bernoulli tells us that this limit's equal to the limit of the function I get whenever I take the derivative of the numerator and the derivative of the denominator. But that has form 1 over 0. Well, what's going to happen, right? So if I take something near 1 and divide it by really, really, really tiny numbers, what I get are really, really, really big numbers. And they're going to be big and positive, aren't they? Because my numerator is certainly positive whenever theta is near 0. My denominator is also positive, right? Again, because I'm working on this side, so sine of numbers in the first quadrant are positive. So this is either approaching positive or negative infinity. It must be positive infinity that it's approaching. And so what we have is that the cycloid has a vertical tangent line here at x equals 0. And if you went through a similar exercise looking at what happens as theta approaches 2 pi from the left, I think what you'll wind up with is negative infinity, which makes sense, right? We have negative slopes, and we're going toward a vertical tangent line, and so I'm going to be going toward negative infinity coming from that direction. So I'll let you do that one on your own. All right, so fine. Let's do one more example. How about the derivative whenever theta is pi over 2? What's your guess? Let's see. Whenever theta is pi over 2, we're a quarter of the way through our cycle. So it's going to happen right about there. Looks like, of course, I don't know how accurate my picture is, but certainly looks like the derivative is going to be positive at least. Let's see if we can evaluate what positive number that's going to be. All right. Well, actually, how about if you pause the video for just a moment? We'll come back and work on this together. Okay. Did you get an answer? Well, This is actually pretty straightforward, right? We have that the derivative, well, we already found what the derivative is in general. And in fact, one reason I'm doing this example is really just to make sure that we all are on board with this notation. Dy dx doesn't really offer a convenient place to put an argument, right? It's not like f of the argument x or f of the argument 2 or whatever, right? We're looking for dy dx whenever our argument is the parameter value of pi over 2. And so this is usually the notation that we use to indicate what we would, that serves the purpose that this serves in functional notation. All right, so here we go. So we're looking for this is incorrect. This should be an x, shouldn't it? Right. So dy dx at the value of pi over 2 is going to be well, let's see. It's going to be sine of pi over 2 over 1 minus cosine of pi over 2, which is, well, let's see. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. And so my denominator is 1 as well. And so we wind up with a slope of exactly 1. And so if this picture had been drawn perfectly accurately, then right at this point, I would have a tangent line that that met with a 45-degree angle with the horizontal. Slope of 1. Okay. Let's ask a different question. What about second derivatives and third derivatives and fourth derivatives and so on? Well, in order to get a handle on that, before we get a handle on it, a common mistake when taking the second derivative of this function, a common mistake is to simply use the quotient rule on this function and say, well, that's the derivative of the derivative. I guess that's the second derivative. The problem with that is what I'm looking for is the second derivative of y with respect to x. And if I just apply the quotient rule to this function right here, to this derivative, then what I'm finding is the derivative of this function with respect to theta. Well, I don't want the second derivative with respect to theta. I want the second derivative with respect to x. So I have to be a little more careful. Let me point out that dy dx can also be written in this way, right? Where d over dx simply means take the derivative with respect to x. So over here, this says take the derivative of y with respect to x. Over here, this says take the derivative with respect to x of y. There are two ways of saying the same thing. So if this is using what we just talked about, if the derivative with respect to x of y, which again can be written this way, is the derivative of y with respect to theta over the derivative of x with respect to theta, well, I could write my numerator here as the derivative with respect to theta of y, right? Derivative with respect to theta of y. So if this is done this way, how should this be done? So let's look at this again. Up here, this says the derivative with respect to x of a thing. That can be done by taking the derivative with respect to theta of the thing over dx d theta. Well, now the thing is the derivative. So if I want to take the derivative with respect to x of the derivative, Well, that will give me the second derivative with respect to x, won't it? Right? That's exactly what I'm looking for. And I'm going to calculate it by, let's see, so the derivative with respect to x of a thing is the derivative with respect to theta of the thing. Well, now the thing is dy dx. And so I'm going to write exactly this down again, except instead of y being the thing I'm taking the derivative of with respect to theta, it's dy dx I'm going to be taking the derivative of with respect to theta. Right? So again, if the derivative with respect to x of y is this, then the derivative with respect to x of dy dx must be this. Right? And so for our example, for the cycloid, I'm just reminding us what the parametric equations are that we derived for the cycloid. We have, well, let's see, we've already decided that the derivative of y with respect to x is this function, this expression. And so it must be that the second derivative, this is how we often write the second derivative of y with respect to x, and you see why we do this, right? That's a reasonable note. It looks like a mess, but it reminds us that, right, if we're asking for the derivative with respect to x of dy dx, then, I mean, this isn't really what's happening, but symbolically it kind of looks like we're squaring a d and on top and squaring a dx on the bottom. So, I mean, this doesn't have any algebraic meaning here, but it's a reasonable symbol to remind us what it is we're doing. All right, so d squared y over dx squared is the notation that we often use for the second derivative. This was developed by Gottfried Leibniz. This was his notation, and it's served us pretty well since about 1675. So here we go. So the second derivative of y with respect to x is the derivative with respect to x of the first derivative. And so that's the derivative with respect to x. And here's the first derivative. And so how did we do that? Well, that's the derivative with respect to theta of this guy over the derivative with, of x with respect to theta. And just carry out the computations. I'll let you go through this on your own. But what we wind up with after a bit of simplification is this expression over here. -1 over the radius of the generating circle times 1 minus cosine theta quantity squared. Well, I want you to notice something. The bottom, so long as it's not 0, is a positive number. The top is a negative number. So what this tells me is that for the cycloid, the second derivative is always negative. Does that agree with your intuition? Let's look at the cycloid again. Do you remember what the second derivative tells us about the graph of a function? Think back to Calc 1. Right? So whenever the second derivative is negative at a point, then the function is concave down at that point. Well, look at this. Everywhere that the second derivative is defined, the graph, in fact, is concave downward. So that also agrees with our intuition of what the second derivative ought to be giving us. And of course, if we wanted to calculate third derivatives or fourth derivatives or whatever, we're just going to continue this process. So the third derivative can be written as the derivative with respect to x of the second derivative. And so we'll just take the derivative with respect to theta of the second derivative over dx d theta, and so on. And that's how derivatives work in the setting of parametric equations. When we come back next time, we'll look at a A few more things that we have done with calculus. Area under the curve, arc length, volumes of solids of revolution. And we'll see how those work in the setting of parametric equations. Until then, stay well, stay safe. I'll see you then.